That first one here. It says, what volume of 0.250 molar nitric acid reacts with 44.8 milliliters of 0.15 molar sodium bicarbonate? So what you have here is a nitric acid aqueous solution reacting with a sodium carbonate, and both of them are aqueous solutions. If you want to put that in there, it just takes up space. And it's going to go to a sodium nitrate, and it's going to go to 8 water and CO2. Now that's going to need a 2 right there to balance that, and 2 right there to balance that, and 679. That'll pretty well balance that equation. Now you got, these are Chem 1 topics. I hate to tell you, you need to be able to deal with that. Now I do have that review on equations online. And so you can go through your equation types and stuff. Now, once you get the equation written, you attach the data, what volume of nitric acid. So what volume of nitric acid, and you've got a 0.250 molar solution. And here is 44.8 milliliters of a 0.15 molar solution. Now, working with moles, we want to convert this to moles and this to moles. Well, from the earlier notations, moles is molarity times volume in liters. Well, I can take this one and convert, liters, and then I'll have that one in liters. But how does that relate to the equation up here? So when I use this expression with this, then I need to look at this as, say, molarity, 0.15 molar times 0.0448 liters. That'll give me the moles of this one over here. Now how does that compare over here? So whatever moles I have here, I have to get this one over here, I have to double it, because as you have a 2-to-1 ratio on it. Hopefully you see that. So I can show you we'll just go that route. There's a couple of ways to work this. So 0.15 okay, we got 0.0067 mole of the sodium carbonate. Well, how many moles over here is going to react with that? Anybody? Okay, anyway, the moles here would be twice over here. And since this is molarity times volume, that's your unknown right there. So you would have how many volumes, liters, is equal to, times, I put that in parentheses right there. 0.25 molar, if you want to do it that way, is equal to 2 times 0.0067 mole, like that. So solve for volume in liters is 2 times 0.67 mole, and that's 0.25 mole per liter, because mole, that's what molarity is, moles per liter. That'll cancel out, and see what we get. Okay, that gives me a 0.0536 liters, or 53.6 milliliters of that 0.25 molar sample, because you converted to moles and you made the adjustments from relative to the standard equation. Okay. So we've got a calcium hydroxide reacting with a sodium carbonate, and that's producing a sodium hydroxide and a calcium carbonate. It's a double replacement reaction. So I need a 2 right there. And let's see, we got 3, 5. I think that's it. Yeah, there. Just needed to, that's all we needed to know. Okay, so what do we have to deal with here? We got 49.8 milliliters of the 0.15 molar calcium hydroxide reacting with how many milliliters of the, let me do it this way, just put the 0.350 molar. We don't know what the volume. That's what we're looking for. So you've got a solution that's with that concentration. Now looking at the equation, what can you say about the reaction ratio? Moles of this one equal moles of that one. So molarity times volume of this side equals molarity times volume of this side. That's what moles is. We know that moles is molarity times volume. And I can leave it in milliliters if both sides are the same. Now, if one side's just moles and the other side, like in the last question, one side's moles and the other side has to be in liters if they're in different terms. But if the volume terms are the same on both sides, you can leave it in milliliters. So this is a 1-to-1 reaction ratio. So the moles of calcium hydroxide equal the moles of sodium carbonate. So that means molarity times volume of the calcium hydroxide is equal to the molarity times volume of the sodium carbonate. And so the volume that we're looking for over here, this is your unknown right there. And so we plug in 0.15 molar times 49.8 milliliters is equal to 0.35 molar, and the volume of the Na2CO3 solution. Solve for the volume of Na2CO3 solution. That's 0.15 molar times 49.8 milliliters divided by a 0.35 molar. That cancels, we're left in milliliters. So we'll see how much comes out of that. And let's see, 21.3 mils. People, you following me? Staying with me? I know this is grueling. How many milliliters of a 0.15 molar sulfuric acid required to completely neutralize 8.2 grams of a sodium hydroxide? So you've got an H2SO4 reacting with some sodium hydroxide, and that's going to make sodium sulfate and water. So making that fit, we need a 2 right there. It's a 2 to 1 in this case. Maybe a 2 here. Yeah. That's 4 and 4, 4, 2, 4, 5, 6, 7, 7, 6. Yeah. Okay, so we balance that one here. So the question is, how many milliliters of the sulfuric acid? So how many milliliters of 0.15 molar sulfuric acid will completely neutralize 8.20 grams? And this is 40 grams per mole. So if we convert this to moles, then we can equate it to this, but that'll be molarity times volume in liters. And then we can come back and convert to milliliters if we have to. So divided by 40 grams per mole, .205, 0.205 moles here, and we need to relate that over here to this one, molarity moles. You can't say they're equal. So we have volume in liters times 0.15 molar. This one is over here is greater by how much? 2 times. This is 2 times greater. So I can actually take this relationship between these two, set them equal, but I can put a 2 in front of this over here, or divide by 2 over here if I want to make them equal. You know, in the equation they're not equal, but in this math I can set them equal. Volume in liters 0.15 equals 0.205 if I put a 2 over here, and that's legal.
And where'd you get the 40? That's just the formula.
That's the formula weight of sodium hydroxide, and I have to divide by that to get the moles. Does that help?
Yeah.
Okay. And so volume in liters is now 0.205. That's molar. That's moles. And that's moles per liter. So the moles will drop out, and liters are the only thing we're left with. So that's 2 over 0.15, and everything comes out in liters. .683 or 68.3 or 683. Oh, that's 683, isn't it? 683 milliliters. It's a lot. Okay. My idea. Okay, here you have a solution of hydrogen peroxide reacting with potassium permanganate according to that reaction. Now, we don't need write the whole reaction out, because the problem depends on the limiting reagent on the reactant side only. So really, all I'm going to do is write down 5H2O2 plus 2KMNO4 plus the sulfuric acid, and that gives products. And that's going to help, because I need to determine in here what mass of H2O2 I react or neutralize or convert in this reaction, and then compare it to the mass of the total sample. The sample mass in here, 20 grams of solution. So you're given a 20 gram solution sample. And what they want to know is what is the concentration of H2O2 in that 20-gram sample. So if once I get the grams of H2O2 out of the reaction, I'll take the grams over 20 times 100 and get a percentage composition. Is that readable? So anyway, and what they say is it takes 51.7 milliliters of the KMNO4, potassium permanganate. So I'm 51.7 milliliters of 0.145 molar potassium permanganate. Now, if you convert that to moles, then you can tell how many moles of this stuff you neutralize. 5 and 2 against X and whatever the moles are here. You can set up a simple ratio that way. Or 5 halves to 5 half of whatever the moles is here. Because this has got to be a bigger number because it's a larger coefficient. But anyway, that's equal to 0.0517 times 0.145 mole of the KMNO4 used. Let's see what that looks like. .0075 mole KMNO4 used. Well, how much of the H2O2 moles was consumed? Well, it's a 5 to 2, so I could, this, whatever's here has to be a bigger number over here. Do you hear me? .0075, I got to have a bigger number over here. Well, I'll take 5 halves of the 0.0075 mole, and that's how many moles of the H2O2 reacted. Because I don't want to take 2/5 because that'll be a smaller number. So the mole ratio gives you a larger number over here, 0.0075. Let me make it look like a 0.0075. Yeah, that looks a little better. Right there. So the number of moles, 0.75 times 5 equals, divided by 2 equals 0.019, I guess, 0.019 mole of the H2O2. And so that's equal to 0.019 mole times 60, 32, 33, 34 grams per mole, and then 0.63 or 64, 0.64 gram H2O2 in solution. Well, the percent H2O2 now is 0.64 over the 20 times 100%. And that's about a 3.2%. That's a pretty standard hydrogen peroxide solution you'd buy at the grocery store. Something like that. Yeah, you got to work problems like this, guys. You got to deal with this. But it's not, if you get the moles concept, in my humble opinion, simplifies a lot of things. Okay, here we're given 6 iron sulfates plus potassium dichromate. They're using chromate for an oxidizing agent. And plus the 7H2SO4, and it goes to products. Now, the idea is to determine what mass of iron do I have. Well, iron sulfate ionizes 100% in solution to iron 2 plus SO4 2 minus. it's going to come apart 100%, like that. So if I can determine the moles of that, I have the moles of iron. And then once I get that times the formula weight, I get grams divided by whatever the ore sample weight is. And that gives me my percent of iron in that ore sample. Yep. Okay. And percent Fe is equal to grams Fe over ore in grams times 100%. Okay, so if you can get it that way. Okay, so what does the problem give us? The strategy is pretty straightforward, just like the last problem. 33 gram ore sample, so our ore sample is going to be not 33, 3.33 grams, and so we need to get the grams of iron out of this. So what do? Let's see what it says here. You're titrating with a 0.15 potassium dichromate. So I can do this again, 6FeSO4 plus K2CrO7, Cr2O7. And so this is a 0.15 molar sample. And we use 43.7 milliliters of that titrin. Okay. So if I get the moles of this, how do I get the moles of that? Well, I've got 0.15 molar, molarity times volume in liters, 0.0437 liters. So what are the moles of that now? Multiply those two together. So 0.15 times 0.0437. 0066. So we use that much of that. So now we want to compare moles of this one to the moles of this one. Well, how much would we have neutralized of the FeSO4? 6 times more, right? According to the equation. So the amount of iron sulfate, moles FeSO4, is equal to 6 times the moles of K2Cr2O7. Well, that's 6 times 0.0066 mole. Now, that's going to give me 0.039 mole of the iron sulfate. Well, iron sulfate, you get that when you also have the iron. Well, the iron too. I'll move that up here for you. So the grams now of the iron in solution is 0.039 mole times 56 grams per mole. That's from the periodic table. I get 2.20 grams of iron in solution. That's how much you titrated. So now the percentage of iron in the ore sample is 2.2 grams over 3.3. Was it 3.3? 3.3. Okay. Grams in the ore sample times 100%. Looks like a 66.1% weight. So that just means it was, the ratio is a weight ratio in there. but everything was revolving around moles in here. And once I get the moles of the unknown, then I convert it to grams, and this from there is percentage, part over total times 100. The entire reaction is HNO3, and is sodium hydroxide. Is a 1-to-1 reaction ratio, producing sodium nitrate and water, like that. Well, the outcome of this is exclusively who's in excess between those two. That's a 1-to-1 reaction ratio. So whoever's in the minimum number of moles is going to be the limiting reagent, and whoever's left over is going to find acidic or basic remaining solution. And so what I tell people is just focus on the reactant side and set it up like this. You're given 35 milliliters of 0.111 molar HNO3, and you're reacting that with 33 milliliters of 0.086 molar sodium hydroxide. Clean that up. Like that. So I need to get it to moles. It's a 1-to-1. So I got to find out what the mole amounts are. They may be equal, but then again they may not. If they're not, the lower number is the limiting reagent because it's a 1-to-1. So it's 0.035 times 0.111 mole of HNO3 plus 0.033 times 0.086 mole sodium hydroxide. I'm running out of room over there. So multiplying those out, I get 0.035 times 0.0039 mole of HNO3, and we're mixing that with 0.0886. That's 0.86 in there. Gives me 0.0028 mole of sodium hydroxide. So when we compare moles against moles in a 1-to-1 reaction ratio, smaller moles is the limiting reagent. It means all of the sodium hydroxide is going to be consumed. And the excess of HNO3 is how much is used over here. Well, you're only going to use 0.0028 of the 0.0039 available. So that means 0.0039 minus what you used, 0.0028 used, in moles is the excess HNO3. Double 0.0010 mole HNO3 in excess. So that's an acid. That's one of the strong 6. That's a strong, and so it's acidic mixture, because you didn't eat up all of the acid. So all the base was converted into sodium nitrates and water, but not all the acid was used. So this is an amount left over. Well, from that, you can get a concentration of the acid remaining. See, that's moles, but you mixed 35 and 33. This is an important little note. So the final solution volume is 35 plus 33 in milliliters. That's 68 mils, or 0.068 liters. And so you got 0.001 mole of acid in 0.068 liters. What's the molar concentration of HNO3 final in the mix? Remember I said little brackets represent moles per liter. Moles over volume in liters. The moles is 0.0010 mole over 0.068 liters. That's 0.015 molar in HNO3. That's the remaining solution concentration of that acid. Because once you get to the moles excess, all I did was just divide by the total volume in liters, and I got the solution excess concentration. So those are the kind of problems you got to deal with, guys, as we go forward in Chem 2. Hopefully some of you starting to register, and I understand the